Então vá, malta, vamos começar. O Pedro já nos fala de coisas giras, não tem nada a ver com aquilo que eu sei, portanto nem sequer vou fazer introdução. Vamos ouvir o Pedro.
Esse é que não sabe.
Exatamente.
Should I switch to English or? Alright.
Não, diz que sim. Só ficar a ver.
Very good, very good. Easy.
Já avisamos, já disse.
Okay. Well, thank you all for coming. What are you laughing? I'm going to be talking about something that's not quite what you're thinking, I believe, because this is not a physics thing. Although this is a MEFT seminar, some of you may not know me, and I'm not from physics, or I was, and I'm not now. Yeah. And so I call this thing Homo Ex Machina, and you'll soon understand why I do so. So the first thing I want to talk about, I'm going to define some things. All right. This works. It doesn't. All right, so I'm going to define intelligence, okay? Specifically biological intelligence. And you can think of this just as just our ability to solve problems, okay? And I'm going to define 4 types of these intelligences, all right? The first one is analytical intelligence, and you can think of it as creating abstractions of the world and learning from past experience. Although all those beneath this one are cumulative, so you can't have emotional intelligence if you don't have analytical intelligence. So you can think of the first one as trying to solve a really hard equation. Okay, so although emotional intelligence builds on top of it, it's a little bit different, because the first one you can have stuff. You can have artificial intelligence actually solving these hard equations. Just throw it in mathematics or something. However, this emotional intelligence pertains to something that is inherently to human agents, or you can also think of it of mammals or something like that. And this is defined as self-awareness. These agents actually know that they exist and they have a state, an internal state, and they can control this internal state. And this is what I call self-management. Building on top of actually, and building on top of this example, you can try to visualize this as if you're trying to solve a hard equation, you'll probably be pretty strained if it's your second week trying to do this. Social intelligence actually pertains to doing the same as emotional intelligence, only to other people. So you can think of this as sort of a quote-unquote mind control, because you can, if I say something to you, then you'll probably change your mind, your state of mind, right? And so building on top of this example, it's dealing with stressed people who are trying to solve a hard equation. And so creative intelligence is a little bit harder to pinpoint. And this is actually what I would say distinguishes us from other mammals. And this is going beyond what is given and trying to think outside the box, all right? And so this is simplifying the equation and put it in spherical coordinates. So it's easier to see. And so having defined biological intelligence, we can actually define artificial intelligence as humans doing it, basically. And so if you want to think about it in these terms, you can define 3 types of AI. These guys called it analytical AI, human-inspired AI and humanized AI. And these are increasing in these types of intelligences. And so I'm going to start by defining what expert systems are, and these really are just boring if and else statement. If this is true, then do this. If you actually build these agents so that they're capable of learning, you get what is called machine learning. And these three things, mostly this analytical AI, has what we are really familiar with when we use neural networks or support vector machines, something like that. It's really just you have a bunch of data and you want to cluster it, or you want to predict something from the future or something like that. There's really no emotional and social intelligence and really no creative intelligence in these systems. And so, obviously, humans have all these four, although with different magnitudes. And the thing that we're going to talk about today are these emotional intelligence and social intelligence aspects. And this is what I'm trying to put into machines, okay? And so, in emotional intelligence, I want to build agents which are risk sensitive. And I'm going to be talking about what that means. And the social intelligence is a little bit harder to, I guess, understand, but you'll see that it's not that hard. It's something called theory of mind. And so before I go on to that, I want to make sure that we're all on the same page why this matters. Here's the list of very simple examples of what is possible with human-inspired AI and humanized AI, and into three different applications. And so, if you really read these things, it's useful and scary at the same time, if this is possible. So, really, what we want to achieve is we want to replace humans from the workplace. That's the end goal with AI. We don't want to work. That's boring, right? So that's the end goal. So risk assessment. If I were to offer you a choice between I will give you €1 million or having playing a game with a coin and you'll get €2 million with 50% probability, and with 50% probability you'll get nothing. Which one of you would choose option 1? All right. Okay. Hmm? No, you just won't get anything in this one. So most people would choose option 1. And really, if you do the math, you get the same thing, right? The expected value of this game is €1 million, right? There's no reason mathematically to expect that people would prefer this one over this one. So this should be 50% to this one and 50% to the other one, right? So, but statistically, people will actually choose this one, like you did. So you're people. Just prove that. And so what I mean by risk is the possibility of losing something of value. Although you didn't really lose anything, did you? This is what you asked. You don't really lose anything, but you frame it such that you may lose something. You lose this €1 million certainty when you switch to the other one, right? And so this is an inherently human thing to do, and this is hard to capture. And so really what we do when we just take the average reward of the other game and compare it to the €1 million, we're using what is called expected utility theory. Okay? And this is a theory about making decisions which are optimal in some sense, in the mathematical sense. And so if you actually want to create these agents which are capable of deciding like humans do, you want to use something which comes from economics or I don't know, psychology, sociology. And these two guys, this is Amos Tversky, this is Daniel Kahneman, these two guys, actually only this guy, received the Nobel Prize on economic sciences. Isn't really a Nobel Prize, whatever. For what is called cumulative prospect theory. And this is a theory about decision making under risk. And so this is something we can use to actually create these things. And so this is a novel thing because most AI stuff is built to perform optimally. We want to create the best clusters of the data. We want to have the best predictions possible. We don't want to make mistakes. However, in here, we do want to make mistakes. We want to make dumb mistakes. But not all dumb is equal, right? We want to make it dumb like people. And so the other part, the theory of mind part, is really something which is only possible with people, with at least two people or more. So this is the social intelligence part of the seminar. And so this theory of mind thing is a psychological concept, which really means the ability to create internal models and to manage them about other people, right? If we're playing a game of chess, and you think I'm going to make a certain move, then you'll probably operate under that impression, right? But if I'm aware that you are aware, then probably you won't do that, right? And this creates this cascade of I know that you know that I know that you know that these machines should take into account, and they don't, because all they want to do is create good clusters. And so these mental states are beliefs, they're goals, they're knowledge, they're all these things, they're emotions, they're all these things that you can actually program into machines. Actually, you can program in sure, but you really want to model how humans' internal models are, right? We are angry, we're sad, we're happy, we're nervous, and so this is an important thing to keep track of if you want to engage with someone, if you want to cooperate, if you want to coordinate, if you want to compete, right? And so this theory of mine is called a theory because these mental states are not visible. They're not observable variables. And using this, keep tracking of mental states, you can actually use this to make predictions. What are people which are sad going to do if they're on top of a building? They're probably not going to do the same thing if they're happy, right? And so this really boils down to what behavior do we want. If we actually put these things into machines, probably the behavior is going to be different. And it's really not really known whether if we build these types of agents, if they're going to perform better or worse. We don't know, right? And this is what I sought out to find. And so to model this thing, I'm going to use this level K model, which is really just a recursive model of I think that you think, that I think that you think, up to a certain level, K, and operate under that assumption. That's just it. And so to summarize, this is really what we want to do. These AI models are built today to perform optimally. People do not perform optimally. People are not rational. People are dumb, but they're dumb in a very specific way. This is what we're trying to capture. And so when we're together with other people, there's this thing called theory of mind, where we model each other. And so if we want to create agents which are able to model risk and at the same time model risk with other people, then we have to use these two things in tandem, this theory of mind stuff and the risk assessment. And so this is what I'm going to do. Actually, this is what I'm going to explain to you. How to create agents with this cumulative prospect theory, the economics guys built, and also with this level K model of theory of mind. There has been some work in this regard. However, they do not use these risk-sensitive agents. They really just use perform optimally and keep track of what the other guy is probably going to do, right? If this guy's goal is going after something, then I should do this. But if this guy understands that I know this, then probably he's not going to do that, and then I should perform the other way around. This is what I just said. And so this is going to have two main parts. First, I'm going to talk to you about game theory and what I mean by cooperation. And I'm going to introduce to you, this is really going to be highly non-technical, so we can just skip the math, all right? This expected utility theory, you've really just seen what I did. Distributive prospect theory is not the most intuitive thing to do, ironically. This is trying to model how people behave, however, this is not really intuitive. At least in this Markov game setting. And I'm going to provide you with an example of a game in game theory, and I'm going to compare these two things. This is still absent of the level K, so no theory of mind up to this point. Okay? And then I'm going to introduce to you what Markov games are, and I'm going to create agents with this level K theory of mind, and then I'm going to put them on a grid, which I will explain, and I'm going to draw conclusions from that. Okay, so game theory is really the study of strategy. Okay, you have agents, and they really want to perform optimally. And there's a set of assumptions that is made in game theory, at least in classical game theory. It's that they're rational, and it is common knowledge that all these agents are rational. And if you want to model people, that's not going to work. All right. Regardless. A game is a metaphor for conflict, okay? And these games are really just a set of agents. They can perform actions. They base these decisions of which actions to take on some information. And they have some motivation behind taking these actions given this information. And really, all games are just these four elements. You change these elements, you get a different game. Okay? You can think of this as the game that I'm about to explain to you, which is really the simplest game you can imagine. But this also applies to games like StarCraft and stuff like that. It's really the information structure and the rewards that change. And so, specifically, coordination is a type of interaction in which two or more agents have to decide on which actions to take, and these actions are supposed to be either corresponding or the same. And so the paradigm example of this is the stag hunt. So imagine you have player or hunter 1 and player 2 or hunter 2, these agents, all right? And they can take two different actions. They can either hunt stags or hunt hares or rabbits. And this is what is called the payoff matrix. So these two fives, these first fives, which is in red, is the reward if both agent 1 and agent 2 both pick stags. So agent 1 would get 5, agent 2 would get 5. However, if 1 goes for the stag and 2 goes for the hare, you can see that player 1 is leaving empty-handed, and player 2 will still get the hare. Regardless of whether player 1 is going for the stag or the hare, he will get the same points, the 1. All right. And so this represents the conflict between individual choice and the common good. The common good is both would actually choose this stag. They would be cool with it, right? They could hunt stags. Notice that this 0 here means that either agent can only hunt stags when they coordinate. This is what I mean by coordination. If they both pick stag, good. If they both pick hares, it's good but not that good. the total reward would be 2, and here would be 10. However, if they somehow pick one of these actions with a certain probability, the total reward would decrease, and then it would increase again. So basically, these things going to these two things, and then going to this thing. So to study these things, these games, these normal form games, we use something called a Nash equilibrium. And really the Nash equilibrium is, at least the deterministic stochastic, the deterministic Nash equilibrium is a set of strategies for player 1 and player 2, or whatever many agents there are in this game, from which none of them will be better off by unilaterally changing. So it's easy to see that this and this are Nash equilibria of this game. Because if, suppose that they would both choose stack, there would be no reason for one to choose hair if he knows that 2 is going for the stack, because he would get a worse reward. And since the game is symmetrical, it's the same thing for agent 2. And the hair is also a Nash equilibrium, because there would be no reason for agent 2, for example, to switch from the hair to the stack, because he would get a 0. All right? So these are the two deterministic Nash equilibria. However, a more interesting approach would be to consider these decisions as stochastic decisions. So imagine that player 1 would choose stack with, I don't know, 12% probability, or something like that. And so really, to get to these probabilities, we can actually use these calculations, and really this is the value for these. Let me start over. So you imagine that 1 assumes that agent 2 is playing stack with probability p. So playing hair would be probability 1 minus p. And so if he has these probabilities, or at least if he assigns a variable to it, then one would actually calculate the value of this action according to this to this probability, and it would do the same for hair. And so if he assumes that 2 is rational, he will choose to play with probability p according to these two values, and he would choose them such that one would have no preference between stag or hare. And so basically what 2 would do is calculate these two values for player 1 as a function of these probabilities, and then choose the probability that equals these two values. All right? Everybody? All right. So if we actually go ahead and calculate this, since the game is symmetrical, we don't care if it's from 1's perspective or 2's perspective. The probability is going to be 1/5. All right? You equal these two expressions, and it's 1/5. What I did here was to use these numbers. And when you use these numbers and use this probability p, what you're actually doing is using expected utility p. This is the way we perform optimally. And so operating optimally would get you this playing stag with 1/5 probability, or 0.2, and the other guy would do the same too. And all right, this is the extent of game theory up to this point. Oh, battery is low, by the way. I guess. Posso continuar? Pode. All right. So let's proceed. So these, to build up what the other two guys did, they actually started in 1950 somethings with a theory called prospective. this was not the one that actually won the Nobel Prize. And you'll actually see why. It makes some really, really dumb predictions, and not dumb like people, okay? So imagine you have this random variable r. Call it the reward. The support, meaning the discrete points that these random variable can actually take, is indexed by these r minus m to r, okay? And so these probabilities that the probability of this random variable to be one of these in the support is of support ri is pi. All right. So you can actually put these arranged in this vector from the least from the r minus m. Okay. So this is sorted. If you sort them and put the probabilities with them, you call this prospect. Okay, this is why it's called prospect. What's interesting about this is that there's something called a reference point here at RK, and so this reference point actually does one thing, which is extremely important to actually what you were trying to say. So you actually viewed those two things with one being a loss, right? So this reference point, yeah.
I was just trying to make the first one.
All right, never mind. So this actually divides the prospect between what is called losses and the gains. Okay, and so under this prospect theory thing, what you can actually do to calculate the value of this reward variable or this prospect is you can sum for all gains the function which I'm going to talk about, which is called the utility function of these rewards, and the weighted, and these utilities are actually weighted according to weights on the probabilities of these outcomes. Okay, and so you have the sum for the gains and the sum for the losses, and you actually divide these two because you have the utility function for the losses different from the ones for the gains. And so this is that utility function. This is for negative r, you actually have the losses, this u minus, and this is u plus. And so the two things you can see here. Okay, this utility function is actually the way you perceive these outcomes. You do not perceive them as being $1 million. Okay, you perceive them as being a function of these $1 million, and these will have something called diminishing returns. These diminishing returns actually tells you that the difference between €1 and €2, mathematically speaking, the same as 1 million and 1 million and 1 euros, but we don't treat these as such because we won't really make a distinction between 1 million and 1 million and 1 euros, whereas we will probably make the distinction between €1 and €2 when we're buying coffee. The other thing which is important to see here is that there is something called loss aversion. This loss aversion actually is translated into this negative part of the utility function being steeper. So we actually are averse to losing things. And together with this reference point, you really are averse to losing things that you probably could have, but you really don't. Okay? And so this is the u plus is the positive part, u minus is the negative part. This w, the weighting function, is a nonlinear weight of probabilities. So actually we don't really see the probabilities as 0 to 1 in a linear scale. We see them as 0 to 1 in this highly nonlinear scale. So this actually tells you, this is the reason why people play a lottery. Okay? We know that probability of being hit by a car is probably higher than playing the lottery and winning, but still we do it because we actually perceive it as being a higher probability. This is their reasoning. Okay, so this is the value under expected utility theory would be you sum these multiplied by these over this entire vector. Under prospect theory, you actually do this weird thing with the utilities, so perceiving it differently with this loss aversion and diminishing returns. and weighing the probabilities such that the low probabilities are actually perceived as being high. And this is supposed to be closer to what we actually do. Okay? So, as an example, if you really take this roll of the die and getting, I don't know, €1 for the outcome of the die, and you perceive it as gains, just for simplicity, you can calculate this value, the value of this thing, this game, and you get this. If you actually use this utility function, which is exactly the same as these two, this one and this one, the utility and the weighting function of these two, you actually get a value of prospectivity of 7.35. And what this really is saying is, if I give you a gift of 7, you will refuse it because this game would be more valuable. And that's stupid, because the higher you can get is 6. And there's no human being which would rather decline a gift of 7 to play this game. And so this is what is formally called first order stochastic dominance. I will not get into that. But what you have to understand is that this is something that the theorists don't like, and cumulative prospect theory actually solves this problem. So the way to solve this is, instead of weighing the probabilities, you weigh the cumulative probabilities, and you subtract them in this form. There's really no intuition for this. You can try and break your brain. I did. So if you, I can't really provide you with intuition on the math. However, the results are more interesting than the other one. So we'll actually use cumulative prospect theory, not prospect theory for the former piece. Okay. So let's actually use this cumulative prospect theory value to calculate the Nash equilibrium, not under the expected utility, but under this new risk-sensitive measure of value. Okay? So if you do the math, blah, 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 you get the probability of playing stack under cumulative prospect theory is 0.028. Whereas with the expected utility theory, you get probability of 0.2. What this means is that this is really risky, because if from the perspective of agent 1, agent 2 will, I don't know, for some reason choose to play hare. This is way too risky for player 1, and so you will probably choose hare with a higher probability. And the same goes for agent 2. And so, in essence, coordination increases, because they will actually be playing the same action, just not the optimal one, but the same action more often, because this is the probability of, 1 minus p squared is the probability of playing, both players playing hare, and this is way higher a number compared when you use this. So you might be asking, well, this is suboptimal, right? But is it really that much worse? If you actually do the math, not really. Instead of having a total reward of 2, you just get 1.95. Because the reason is there will be less times where only one of these goes for the stack and gets 0. And so the common good is really not that much worse. Individually, they will be much better. Okay? So this is the first result of using this cumulative prospect theory to analyze cooperation. Actually, coordination. Operation is different. And so we've taken a look at what coordination means and this game theory stuff, and we've actually seen that using cumulative prospect theory actually increases these coordination. So now what we're going to do is taking a look at coordination over time. And to actually study this, we're going to use something which is not a normal form game, which is what you actually saw, where there are agent, action, rewards, and the information is they really don't know anything about each other. They just assume that they're rational. So one player doesn't play and the other guy goes afterwards. They really just play instantaneously. So to actually model these things, but taking account time, which is a really important factor for reasons that we'll see in a little bit, we're going to use something called a Markov chain. And to explain Markov games, I'm going to have to explain to you what Markov decision process is, and then introduce agents into a Markov decision process. But you probably don't know what a Markov decision process is, so I'm going to have to explain Markov decision process. And to explain Markov decision process, I have to explain Markov chains, and then add actions and rewards. And so I'm going to explain, okay, actions do include control and rewards include motivation, and then these Markov chains is what I'm going to start in, and then I'm going to work my way up. I'm going to try not to take my the whole of time in this, okay? So, but really the math here doesn't matter. The intuition is what matters, okay? So I'm going to focus on that. So Markov chain is a sequence of random variables, and they actually have this property which is called the first order Markov property. And this property, what it means is, if you want to know the S sub t, so one of these random variables, all you need to know is S sub t minus 1. The rest doesn't matter, okay? So what this really means is the future depends only on the present and not on the past, okay? And so let me give you an example instead of going through all the math. What this means is if you have this state space, which is state 1, state 2, and state 3, you put it into this diagram. These arrows mean going from one state to the other, and these numbers are the probability if you, for example, stand in state 2. The probability of going to state 1 is 0.1, and the probability of going from 2 to 3 is 0.9. And there's no probability, there's a zero probability of going from state 2 to itself. Okay? So, the first thing we can do, actually what is done, is put these Markov chains into what is called a transition probability matrix. And really, these numbers that are in this matrix are really just these ones. And the rows and the columns of this matrix are sorted according to this state space, 1, 2, 3. And so this number here is the probability of going from state 1 to state 1. So it's this number. So the next thing is really if you have some state vector. So if you, for example, know that you're in state 2 and you want to know where you're going to end up or where the system is going to end up, you just multiply this row vector with this probability matrix and you get a different vector. And so if you actually keep doing this to infinity, which you can't, or really you can really just use the right eigenvalue and eigenvector, you're going to get into what is called a stationary distribution. So this is regardless of where you start. If you take this system, which is there's really no control in it, it just evolves over time, and really just get this going. The system, you're going to look at it, and the system is going to be on state 3 with probability 9 over 12, and so on and so forth. So if we add actions and rewards to this Markov chain, you get what is called the Markov decision process. This is the example that I had before, only with, there's really now two probabilities on this transition and this transition. There's numbers, there this minus 1, 0, and plus 5. And what these are the rewards of being in state 1, the rewards of being in state 2, the reward of being on state 3. And so you can do this again, but now you have this transition probability matrices because you have two actions. You have the action going to the left or going to the right, which changes this probability. So in essence, choosing an action is actually choosing in which Markov chain you really want to navigate in. And so this adds control. And the reason to have control in this is really just to get the highest reward possible. Okay? And so this choosing of actions is what is called policy. So you choose each action with according to some probability. And giving you a policy, if you actually fix this policy, so imagine you would play left with probability 1 wherever you are. You would fix a Markov chain, which would be only with this number here and this number here, and you would discard the L choices, the L probability. And so the problem here, as I said, is finding a policy that maximizes some value, which is a function of these policy, and this policy is a function of S, so that's why it's called a function. And so under expected utility theory, what we want to maximize is this expression. So you have here the expected value over the dynamics of the system. You have the sum of the discounted rewards from time equals 0 to all the time. Okay? So this beta here is called the discount factor, and it's power to the t. And this discount factor is a number from 0 to 1. So this means that this will actually converge. If you don't have this, you would have to have some restriction on these state spaces, like, for example, going from here to a state which has a probability 1 of going to itself and having a reward of 0, for example. So this wouldn't like explode. Okay? So this is what is called an MDP. Everyone which uses MDP does something of this sort. However, if you actually want to use this cumulative prospect theory, things are a little bit hairy. But let's just go through it anyway. So this is the value. If you give me a policy and a certain state, I would be able to theoretically calculate this. I'm not going to go through it because it's really boring. Just take a look at it. All right. So, so you'll have to trust me that this actually represents the way that cumulative prospect theory operates in a Markov decision process. All right. All right. So, what we really want to do is maximize over this by picking a policy. And so, this policy that maximizes this is called the optimal policy. So, as an example, take one hunter and two types of prey. One prey in state 3 and another one in state 11. In state 3 you have hares, which gives you +1. In state 11 you have +5. And everywhere else you have 0. Obviously pigs are fatter than the hares, so they provide you better reward. And so if you formalize this, blah, 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 you have 3 actions, left, staying, right. You have these 3 transition matrices, so actually you don't really have, if you pick left, it's not necessarily true that you will go to the left on this chain, but you will try, right? In some probability you will either stay where you are or go to the actual other direction, okay? So there is some stochasticity in the environment. And so you can really plot this really, the rewards of this as like this. And once you actually calculate those two values, the value under expected utility theory and the value according to cumulative prospect theory, you get these two things as a function of the value. Okay? So as if you use expected utility theory, the value increases up to 3, but then decreases a little bit, and then goes to the maximum here, and just decreases here. So this 3 here is this 3, and this is the pigs, which are fat. So there's more value on it. And so the difference between the two things actually prescribe a different optimal policy. So the optimal policy in the sense of the expected utility theory is the optimal according to the mathematical thing. So in the cumulative prospect theory is optimal in the sense that it maximizes that entire expression, which I will not provide any intuition. Okay, and so really we can actually see this really doesn't tell you much other than the cumulative prospect theory gives you a higher value overall. But really this little bar here actually says that it is optimal to choose stay when you're in the hares. Whereas if you use cumulative prospect theory, you really just go right. You stay on this 11 on the pigs, and then you go to the left if you went too far. So these two things actually prescribe different behaviors. Okay, but what we really want to see is how these agents, which are now capable of measuring risk over time, actually behave when you put them together. Okay, so we're going to create something called the Markov Chain, and it's really Markov decision process with more agents. And it really just you have a value for with an index here, with which is the value of agent I, and this agent I has some weighting function and utility functions. And so really you just have to sum over what you think are going to be the actions, so the policy of the other agents. But you really don't know this, right? This is the problem. With game theory, you would actually just assume they're rational, calculate those two things, and actually say that since the game is symmetrical, you would get p with 0.2. Okay, can't really do that here. So if you actually put this thing, you collapse this such that it's really just a function of this epsilon, which is what we're trying to integrate with this integral here, you get this. So this is just this easy on the eyes. And so this is, if you take a look at this and compare it with what we had before, it's really just the same as having a single agent if you give it the policies of the other agents. So it's exactly the same, playing with one person or alone, or with, I don't know, 100,000 agents. The really, the hard thing to do really is getting these joint policies, so the behavior of all other agents, and then you just consider it as part of the environment, right? You assume that these agents are part of the environment, and so really I'm just playing alone, and this environment is playing against me. And so the dynamics of the system really just change, okay? And so if we don't have these, you can just assume them. This is what the level K hierarchy stuff is for. And so how this works is I'm going to use this with a two-agent scenario, and I'm not going to go any further than that because things get a little bit weird, except exactly with this model. And so this goes as follows. So you have two agents. Agent 1 assumes what I call the stereotype policy. So the policy of order 0 for agent 2, and agent 2 does the same for agent 1. So each of them assume that they're gonna, I don't know, play randomly or something, okay? Given these two policies, agent 1 can actually create this value because he's assuming this one, the policy of the other guy, the behavior of the other guy, and behave optimally and create this first order policy. However, agent 2 can do the same. So he has a first order given that agent 2, actually agent 1 was playing with some assumption policy. Okay? However, if agent 1 is able to calculate this one, he's going to probably do the same, except using this assumed policy, he's going to use this one instead. And so this is what I call the second order policy. Okay? Agent 2 will do the same. And this repeats to some order K. There you go. This is the level K hierarchy model. And so this level K actually prescribes a different policy. And so we can really take a look at this as we did before. We can take a look at it as a function of these different orders. Okay? And so to recap, we've seen what game theory is. We've seen what cumulative prospect theory can do to improve the coordination of normal form games. We've taken a look at decisions over time. We started with the Markov chain to describe discrete time stochastic environment model. We've introduced agents and actions to this, and we've seen that the behavior of these two theories, these two types of calculating value, prescribe different ways of behaving. And so, and that CPT allowed to escape that Hare maximum, local maximum. And so we're now going to take a look at what happens if these agents are actually put together and they actually do something similar to the stag hunt, only over time. And so if we frame it much in the same way as we did before, but now with two agents, and now you have hares on number 3, and instead of pigs you have stags, and everyone knows stags are smarter than pigs, okay? So these are only able to be caught as, you're snarking, okay, you disagree, maybe. Okay, so these stags are only be able to be captured when these two agents are actually on state 11. Okay, so these two agents will be running around here. You won't see anything of the sort. You won't see simulations. You will actually see those stationary distributions. Okay, and we will draw conclusions from that. Okay, so this is the same dynamics of the system. So this is for agent 1 and agent 2. And these are, instead of putting it as these numbers below these states, you can actually put it like this. So this blue thing is this phi, but it only works when agent 2 and agent 1 and agent 2 are actually on this on state 11. The same for agent 2. This is reward for agent 1. This is reward for agent 2. And this line here is the reward for agent 1. Regardless of where agent 2 is, you will always get a reward of 1. Okay? So, and this is transposed for the other agent. So, these two things are actually the same thing as I have here. Okay, so if you use the value under expected utility theory, what you'll see is that this is a value for agent 1, but since the game is symmetrical, again, these are also the values for agent 2. Oh, no problem. So this is for a policy of order 1. So here, agent 1 is assuming that agent 2 is performing randomly. So he will choose left, stay, and right with a third probability each. And so this is the optimal value for that assumption. And here is actually using instead of assuming that he's random, he's using the assumption that agent 2 is actually performing optimally, assuming that agent 1 is performing randomly. Okay? And so this is the same thing, only with order 3. So as you can see, with increasing order, this thing is getting slightly darker, okay, slightly redder. And so this means that this was actually proven before. So this is not anything new. It's interesting. This is what got me into this thing, but it's not anything new. What is new here is, and so the summary of this is that as you increase the sophistication of these policies, the value of the stack state is increased. Okay. If you actually use cumulative prospect theory, this is the same thing, only much more dramatically. And it's obvious that here it's even in the first the first order assumption, it's already way larger than the expected utility theory. And so this actually tells us something about whether risk is important or not, and theory of work. Okay. And so if you compare the policies, this is the black which is supposed to be dark red or whatever. So this black is the probability 1, this is probability 0, and what you're actually seeing here is for expected utility theory, the policies under the assumption that agent 1 is using a level 1, a level 2, and a level 3, so the verticals you saw before. So this is the optimal policies under expected utility. And so you can actually see, to summarize this thing, this little bar here says you should stay when agent 2, so agent 1 should stay when agent 2 is in between this state and this state. So state 14 and state something. And this bar actually starts to increase when you increase the level of sophistication. And so when you bounce these policies back and forth using this level K hierarchy model, you see that's basically what you saw with the values. Okay. What's interesting when you actually compare it with the cumulative prospect theory, this bar actually goes all the way down. So you will actually always stay, regardless of where agent 2 is, it will stay in state 11. You will not move. Okay. So this prescribes already a very different way of behaving. And so, as I said before, if you have a Markov decision process and you have the policies, you actually get a Markov chain, and you can calculate the equilibrium distribution. You can do the same with the Markov game, giving the policies of everyone. Okay? And so you can actually visualize this if we put this system into whatever state, into whatever initial state, and you let these agents run around. When time tends to infinity, this is the probability of finding both agents in state 3, and this is the probability of finding both agents in state 11. And so this is for order 1, order 2, and order 3. So here, both agents are using an order 1. So each of them are assuming that the other one is actually using a policy which is uniform. So left, right, and stay with 1/3 probability each. And that's not the case. They're both using, they're both assuming that, but neither of them are actually doing that. And so if you actually do that, they will both, you will find them with a very high probability on just hunting hairs. Okay. And so this little dot, if you can see here, I don't know if you can see it, this actually starts to increase, but it really doesn't go. When you actually calculate this to an arbitrary order like 10, it really, up to the 3rd or 4th, really doesn't change anything. And so if you compare this with the cumulative prospect theory, you actually get very different results. And so what this shows is that when agents are actually behaving suboptimally in the mathematical sense, when you put them together, they're actually performing much better together, right? So you get an overall reward of 10 at each turn, at least they're hoping to, and you won't get the same results with expected utility. So that's really what I wanted to talk to you about. If we actually put these agents with, if you actually imbue these agents with these new, actually this isn't really new, but whatever, these economic perspectives of how people are going to behave, you're really going to get different results. And what this really says is that maybe we shouldn't be using game theory to actually create models to, I don't know, stuff like climate change agreements, model stuff like that. Or modeling how a group of people around a person which needs help, if they're actually going to help or not. Stuff like that. So when you're using game theory with agents that represent humans, you really shouldn't use expected utility theory. You should use something which measures risk and many other cognitive biases that humans have and robots really don't yet. Okay, so that's it. Thank you. Any questions? Go ahead.
When you are using prospect theory, you define that some outcomes are actually negative.
Yeah.
But how do you define them? Is it through expected utility, or because, for example, when you roll a dice, even if you win, if you always win something, if you just win 1, 2, or 3, you are actually losing at the game because the average should be around 3.5.
Yeah.
Right.
Yeah.
So how do you model the what's bad and what's good?
Right. So everything
because it seems like a core part in the theory.
Yeah. Yeah. So you're asking how to calculate the reference point, right? Okay. So what I use here, since all my experiments were actually with positive reward or 0, a non-negative reward, I didn't really have to calculate anything. And really, I could have just used this reference point to be anything you would like. Okay. Obviously, these results would change. I probably would get different results, and so this is why there should be a lot more work on this. But really, there's no theory behind, at least no mathematical provable theory as to what is a good reference point, because people frame it as they want, right? And different people frame it as they want. And so if you really want to go that path, you have to have some sort of personalized model which calculates these reference points. Really the way that I showed you this first game with the option 1 and option 2, If I had changed you with the other way around, or with different, I don't know, €1 and €2, or something like that, you would use the probabilities of choosing each option would be different. And so, do it however you like.
It's just that it influences, like, for example, the €1 million case, since you have the theory that the base value would be 1 million. If you are actually seeing the lottery, the 50-50 lottery, the 0 would be minus 1 million.
Yeah.
And in that case, since you see negatives as being worse, it would be like minus 1.5 million.
Exactly.
And the positive just 0.5. So in that case, a simple non-cumulative theory would work, kind of. But still.
But there you have a comparison between one
there's another
deterministic one and the random one. If you have two random ones, what do you do, right? It's not really. If you can actually use expected values of those two things and use it as the reference point, but sure, you can do that, or just set it to 0 or 1 million, or depends on the person. So, any other questions?
I have more of a comment, kind of related to the reference point. If you were to ask the same question of the 1 million for sure, or the 2 million 50-50, even if it was 2 million 80%, I would still go for the 1 million for sure.
Yeah. So that changes the utilities and the weighting that you do on the. So again, it's not really the reference points only that matters. Different people have different utilities, and really, if you were a billionaire and you were playing this game, it would be like, I would take the risk. I could pay it, right? I could, quote unquote, afford it, right? You wouldn't lose anything; you just lose the opportunity cost, right? Right. Yeah.
How do you test if your theory, the results you have are right?
Yeah. So actually, cumulative prospect theory has been studied throughout the years, and it actually, I'm not showing you any results here, but there are a lot of evidence that supports that humans actually use cumulative prospect theory when you use something like the maximum likelihood estimation of parameters instead of the expected utility theory. But again, it may be that since cumulative prospect theory has more parameters and expected utility theory does not, maybe that's why. I don't know. Just pick this. Yep.
So, ultimately, people use this to model markets, right?
Yeah.
To model people.
People use it in marketing and finance. And markets. And some people have introduced this into the first part of the talk where they actually put in games. So it's a little bit more formal. But yeah, there's a lot of applications. I didn't really show anything. I just wanted to show what was mine. And yes.
And what about, because this is kind of an empirical...
yes, it's a heuristic model. Yeah.
What are there any approaches that try to drop all the heuristics and just put a big neural network and try to predict people behavior?
Yes, actually.
Is that happening?
Yeah, it is. It happened 7 days ago.
Really?
Yeah, there was a paper coming out that used this giant data set of judgmental decisions of people, and they trained a neural network using what would cumulative prospect theory do. And so that would be the output of the model, and they trained with the input and the output, and they got a neural network which would I don't know really how much accuracy improvement there was, but it was state of the art, so it was better than anything else. So it really isn't that hard to make things that behave like people if you actually use these models as heuristics and then use it on real data. So here I'm not using anything that's real data, but again, this is just a model. I use these. So I use these baselines. So this is the reference point of 0. I use this discount factor of 0.9. I use linear utility functions. So I didn't really use the diminishing returns, and I use there's no loss aversion here. There's no diminishing returns. So this is really just the weighting of probabilities that's different. And so only with this you get these results. Okay. So I actually use these things because this function is used throughout the literature, and this one was I really just wanted to compare how just weighing probabilities would be different and to get these results. But again, these two functions and these two things are entirely arbitrary. Right? These two make sense. So these make sense. These fits like well with the theory. This one doesn't. But I really just wanted to compare the models. So if you actually use this model and then introduce something like instead of calculating this this entire thing, which was really pain in the ass to do, with a neural network, so you would have something called a value network, and then use it with a policy network, and use some cumulative prospect theory to inside those things. You would have something which would be behaviorally plausible neural network or something like that. There's actually something cool using physics. So you have these neural networks with a term which increases the loss of having something which is nonsensical in physics. Like you have temperature on a lake. You know that the pressures, for example, on the lake are increasing. And so if the model would predict something which would not sort it, you would give a cost to the network when it was being trained. So it would be something similar using these things.
The neural network and what was trying to learn what was for what was the
on what example? The physics thing or the the physics one?
The first one.
Okay, so the physics one. No. Which one was it?
The one you said.
Okay, so the one I hypothesized.
Não, aquele que disseste há 7 dias atrás.
Oh, right. Yeah. So that's just, from what I understand from the abstract, I didn't really read the paper. So what they were trying to do, they had this giant data set of judgment calls, right? Decisions that people make every day, or something like that. Or in court, or in roads, something like that. And to actually decide whether these two or more, I don't know, decisions are the best, they used cumulative prospect theory, or I think they just used prospect, not cumulative prospect theory, and to calculate the outcome, and created the outputs according to cumulative prospect theory, and then they just used the neural network using those things. And then they evaluated it on a separate data set of also judgment calls. They achieved state-of-the-art. Anything else? Okay.
Machine. Bora lá.
Não,